So we have here the NOR gate 74LS02. So it is the complement of the OR gate, and output is 1 if both inputs are 0. So we have here the symbol of OR gate, okay, with inputs 0 or 0 and then complemented. So as you can see, if I have 0 or 0, 0 or 0, that is 0, right? So 0 or 0 is 0. So 0 or 0, that is supposedly 0. But since this is complemented, so therefore we have here the 1. And here we have 0 or 1. So 0 or 1 is 1. This is complemented, thus we have 0. Then we have also 1 or 0. 1 or 0 is 1. This is complemented, thus we have 0. And then we have 1, 1, which is 1. It is complemented, thus we have 0. So as you can see, that is the complement of OR. Because yeah, it's a complement of OR. So NOR gate 74LS02 can implement the NAT gate with the two input NOR gates of values 0 or 1. So in this case, we have here the NOR gate with both inputs, so with both input of the gate connected to the input values. So if I have here 0 or 0, that is 0, complement, that will be 1. So 0 or 0, that will be 0, but 0 complement is 1. So have your input of 1, so if I have 1 or 1, that gives me 1, but complementing that gives me 0. So NOR gate 74LS2 can also be used to implement AND gate by first complementing the input A. So we have the input A, the first input, complement that, and by complementing input B and applying the NOR gate. Okay, so as you can see, we have here, have here 1 or 1, that is 1, complement, that is 0. So 0 or 0, complement is 1. So 1 or 0 is 1, the complement of 1 is 0. So or for the inputs, then complement. So implements AND with inputs 0, 0. So we have here the De Morgan's theorem of the NOR gate. So for you to be able to implement AND using NOR, we will be using the concept of the De Morgan. So De Morgan's theorem says that you have to invert input and invert also the operation. So that means if I have here an AND operation, so A and B, so you have to invert the inputs, thus we have A invert, and invert the operation, thus you have the plus, and then you have the B, and then you have the final NOR gate, so that is the De Morgan. Okay, so the final gate for the NOR gate. So in this case, let me just clear my pen. So we have here 0 or 0, that is 0. So complement of 0 is 1. So 0 or 0 is 0, complement of 0 is 1. So we have here 1 or 1 is 1, but the complement is 0. So implements AND with the inputs 0, 1. We have here 0 or 0 gives 0, and then complementing that gives 1. So 1 or 1 is 1, complement is 0. So thus, for the final NOR gate, so we have here 1 or 0 is equal to 1, and complementing that, that will become 0. So as you can see, we have here 0, 0, 0, and 1, which is, what's the value? That is 0. So implements input and for inputs 1, 0. So 1 or 1 is 1. Complementing gives you 0. So 0 or 0 is 0. Complement is 1. So the last NOR gate will be 0 or 1 is 1. Complementing that is 0. So lastly, we can prove that NOR can be used to implement AND with inputs 1, 1. So here we have 1 or 1 is 1. Complement is 0. 1 or 1 is 1. Complement is 0. So 0 or 0 is 0 and complement is 1. So thus we have 1 and 1 is equal to 1. We can also use NOR gate to implement OR. So OR inputs A and B, and then complement the operation A or B. So we have here inputs 0, 0. So A and B inputs. So A or B complement A or B complement, so which is this part, and then complement the whole equation. So for example, we have input 0, 0, where in 0 or 0 is 0, complement is 1, and then 1 complement is 0. So simple input 0, 1, so 0 or 1 is 1, complement is 0, and then again complementing that will be, gives us 1, which is true. 0 or 1 is 1. And we also have for inputs 1, 0. So 1 or 0 is 1. Complement is 0. And complementing that again gives us 1, which is 1 or 0 is equal to 1. And lastly, for inputs 1, 1. So 1 or 1 is 1. Complement 1 is 0. Complementing 0.